Okay, welcome everybody to the ZAC seminar. Okay, today we have Professor Stefan Kebekus, and he will talk about the Brauer-Manin obstruction on a simply connected fourfold.
Thank you so much. Thank you for the introduction, and thank you for the invitation. It's a great pleasure to talk here. And also, I have to say, I'm not giving these talks very often online, and I'm not used to using Zoom, so this is still very exciting. Right. Let me start by laying out a motivating goal of this talk. Maybe it's not the final goal of what we are doing, but it will show what eventually application we have in mind. So the goal, I look at the field, typically is something like FB and then rational functions in one variable. And with that field, I would like to construct a geometrically simply connected surface, say Y of general type, fiber it over P1, Y to P1 of K, such that if I take the set of rational points, I take the image, then this is not empty. I do want some honest rational points, but I want this to be finite. So in particular, all the rational points that exist, they're concentrated only in finitely many fibers. And to the best of our knowledge, that would then be the first simply connected example. So first one connected surface over a global function field. Where Bombieri-Lang is known to hold. Maybe I should point out that over number fields, there are examples, but those examples are conditional to the ABC conjecture. So, to ABC conjecture. Right. So why is this interesting? If okay, because of this Bombieri-Lang conjecture, but you can also take this one step further and apply some ideas of Boonen. So following Boonen, one can then find a family, very explicit family of Chatelet surfaces say S over P1, such that when I take the fiber product, so S times P1 times Y, then I get another simply connected variety, this time with no rational points at all, but with a Brauer-Manin space, not empty. And again, to the best of our knowledge, that would be the first simply connected a variety over a global field, global function field, I should say, where the Brauer-Manin construction cannot explain failure of the Hasse principle. Of course, these examples have a long history, and there is a family of examples going back to the work of Björn Kuhnen. But those examples, they are always fibered over a curve of rational of general type. So they are never simply convected. And then to accommodate Kuhnen's example in the theory, Skorobogatov has devised his étale Brauer-Manin obstruction, which explains the failure of the Hasse principle for those examples. But then our example is simply connected. So the Skorobogatov étale Brauer-Manin obstruction does not add anything new here to the classic Brauer-Manin obstruction. So in that sense, also this example is new. Maybe as a last remark, our construction is quite explicit. And what do we construct? Well, we need to ensure that we pick a family of Chatelet surfaces, so very explicitly given surfaces with very simple equations. And we need to ensure that the Chatelet surfaces they have no rational points over phi of y of k. So that will then ensure that the fiber product has no rational point at all. And then one need to compute the Brauer-Manin space. And for this, I will say next to nothing, except that this is something that I am not really the expert in. This was the job of Arne, who did his PhD with Collioure-Tillene and knows how to do such things. So for this talk, let me rather concentrate on the construction of the surface Y, which is where the contribution of Georges and myself come in, and not go into the details of the Brauer-Manin construction here. So right, then how can one possibly find a surface over a function field where we can say something about the set of rational points? And the idea goes back to Campana and Stopino is this. We look at a tower of varieties like I have drawn. So we start with the projective space. Inside the projective space, we take an open S0 that needs to be constructed suitably. And then we look at P1 cross S0, call this X0, and this map then here is pi naught. This is pretty boring, but then we construct, following a paper of Stopino, a threefold Y0, or if you wish, Y is a surface over the function field, and that has interesting properties. The properties come from a divisor, so we construct a tower of varieties over Fp and a divisor D0 that lives on X0 such that the following holds. And let me indicate the divisor here. This is our divisor D, and the pre-image in this picture is this surface here. So that's how I think of this. Right, such that the following properties hold. So first, I have X naught that is fibered over S naught. The fibers are P1, of course, is the product. But the divisor D naught, of course, on every fiber specifies a finite set of points. And I would like that this family of pointed curves, this is not trivial. I would even like that the Kodaira-Spencer map does not vanish. So viewing X naught, D naught as a family of pointed curves, and the Kodaira-Spencer map is not trivial. So this is one thing that I would like to have. Also, I would like to say a little bit about this yellow surface. Namely, if I take the pre-image of the divisor D and I look at its support, then this is simply a product of D naught and a one connected curve. In Stofino's construction, this is actually a tree of rational curves. So the fiber is generally a tree. The fibers will have multiple components, and it's simply connected. 3, I would like to say that at the level of function fields, there are no multiple fibers over D naught. So the fiber over the generic point of D naught is not multiple, but at the same time, I would like that all components, oops, can I move this out of the way? Okay, all components of the pullback divisor have coefficients at least 2. So what does that mean? I said that there are no multiple fibers and all fibers have coefficients larger than 2. By this, I mean that I could have like one fiber component has multiplicity 2, another fiber component has multiplicity 3, and then this does not count as a multiple fiber. Okay, then there are some more things that we would like, but I'm not going into any details here. But let me point out that these assumptions will guarantee that Y naught is simply connected. The family, we have fibers that are simply connected but not multiple, and that can tell you something about the fundamental group of the full family. Details I would rather not discuss, but I hope this is plausible enough at this point. But something that I would like to discuss in more detail is now the question, what about rational points? I promised that to construct a surface over the function field with very few and controllable rational points. So what about rational points here? And the central observation is the following. Given a k rational point, and a k rational point is the same as the section gamma from S naught to Y naught. So let me draw this section here. This is the section gamma, and the image of the section will generally look like so. So then I can compose this morphism gamma with a phi naught, and I get a section from x naught to y. So and I look at the image of this. So this is gamma composed with phi naught. This is now a curve in x naught. And this curve is, well, either it is contained in the support of d naught, or it touches d naught tangentially, but never transversely. And this is because all the components of this yellow surface that we have in y naught have higher multiplicity. So the image of my section will typically look like so. And here I have an intersection point of higher order. So in the language of the trait, we would say that this composed morphism is a Campana integral curve. And why have I been telling you all this? Because the main statement that I would really like to discuss, and this was the motivation for it, is the statement that there are hardly any Campana integral curves. So the statement is a theorem that we call an orbifold version of the Mordell theorem in the function field case, which says only finitely many C integral curves exist. And that's the statement that I would really like to discuss. Everything so far was motivation. And this is where I'm going to spend the remaining time of this talk. By the way, are there any questions? That will be a great point for it. Okay, I can't hear any. So then let me start to be a little more precise and say precisely what our setting is and what finiteness results I would eventually like to show. So the setting is this. I take K an algebraically closed field. So far, we have been working with a global function field. But of course, when you want to prove a finiteness result, you can just as well pass to the algebraic closure and prove finiteness there. That's a stronger result. So I am happy to assume algebraically closed from now on. We have an algebraically closed field. We have a morphism. This is a K surface fibered over a curve. A K curve. We have a divisor. This is now a Q divisor on the surface X. So, and this is supposed to be a divisor with standard coefficients. Standard coefficients. So D is a divisor of the form 1 minus 1 over mi di, where mi is a positive integer, or could be infinity, and then 1 over infinity is 0 by definition. So the pair x comma y is what Campana calls a geometric orbifold. Then secondly, we have an open set S naught in S such that the following holds. And maybe I should also draw a little picture. So here's my surface X. X is fibered over my curve S. And I have the divisor D. And as before, let me draw this divisor D in yellow. So here's D. So what we want is that D naught over S naught is etal, which in characteristic P, of course, is a strong condition. This means that the components of D naught are smooth algebraic points. So we want this morphism to be separable. And I would like to ask that the degree of the relative canonical of the pair is positive on general fiber. And I want that the Kodaira-Spencer map does not vanish. And I will later seriously need this. You could ask, is an orbifold Mordell theorem or a Mordell theorem in the function field case, is it actually correct if you have a family of curves that vary in moduli, but the Kodaira-Spencer map could be 0 because the moduli map might be inseparable? And the answer is, it's known that no Mordell theorem can possibly hold in this setting. So we definitely want non-vanishing of the Kodaira-Spencer. So this is the setting, and the central definition is that of a C integral curve. So an S morphism gamma from a curve T to X is called a C integral curve if, well, T is a curve, obviously. Gamma is birational onto its image. Onto image, we have that the image of gamma is not contained in the support of D. And I want that for every closed point of my curve over the open set S naught, the multiplicity of the pullback divisor DI at the point T is at least MI, or it could possibly be 0. So that means if my divisor D has, say, multiplicity 1/2, so, and I have here a set S naught, which is everything but this marked point, then my curve must look like so that if it touches the yellow curve at all, then it must always intersect tangentially, except at this one point where it's allowed to intersect transversally, or maybe the curve is singular at that point. Anything can happen. But outside, so at a point like this one marked with an X, Outside, I always have local intersection multiplicity 2, 3, 4, 5, or more. In particular, a 3 is allowed. I'm not asking for a multiple of 2. So, and the definition is that the morphism gamma, this is what's called a C integral curve. So a C integral curve is really a commutative diagram like this. I start with a curve C, I map it with gamma into the shift X, and the image curve is supposed to satisfy this tangency condition. And in that statement, in that setting, I would like to give an idea of the orbifold Mordell theorem, which basically says in this setting, given a curve T, I have only finitely many C integral points, integral curves of the form gamma from T to my surface X. Right. That is the main statement. And the main ingredients are, well, always the same in this business, right? The main ingredients to prove a finiteness statement of this setting are height bounds, which then quickly imply boundedness and deformation rigidity. Right. And we are mostly interested in the case of finite characteristic. And it's not very hard to see that in characteristic P, in positive characteristic, height bounds imply rigidity. If you have a non-rigid family, then you can pull off some Frobenius tricks and obtain an unbounded family of curves. It's not very hard, but I would rather not go into any details of this right now, and simply say that the interesting thing to look at is really the height bound. And once you have the height bound, at least in characteristic P, then you have everything. So I should now turn to the height bounds. And the statement is this, which is something went away. I have h of gamma, and I need a square root here. So this is, these are many, many symbols. Let's look at this theorem, what it actually says. So we start with a number epsilon, and then all C integral points are supposed to satisfy an inequality. The inequality involves the height, which is meant to be small. And on the right-hand side of the inequality sign, I have a coefficient. This is this maximum something, and then delta, which is called the discriminant. So what is height? What is the discriminant? You see it here. The height is this, which is essentially the intersection number of the relative canonical with our curve T. That's what the height is, the intersection number of the relative canonical with a curve T, and then it gets divided by the degree, but okay. And on the right-hand side of the inequality sign, there's the discriminant, and the discriminant is this, which is essentially the genus of the curve T. So we want to say that the intersection number of the curve with a relative canonical is small when compared to its genus. That is a statement of the height bound, and the rest is this O of square root, and okay, this is technical and has nothing to do with the core of the issue. So we want that the intersection number with relative canonical is small when compared to the genus. And then there's this factor or this constant, this maximum. This is essentially the degree of the canonical bundle on the general fiber. But maybe we just ignore this and call it a constant for the purposes of today. But a few remarks are in order. Remarks. So first, over the complex number of Campana has Mordell type theorem without height bounds. So these height bounds that we are proving here, they are really only interesting in positive characteristics. Then I should definitely say that the theorem is far from optimal. Optimal over the complex numbers. Again, I feel that this theorem is mostly interesting in positive characteristics, so I don't care so much about what happens over the complex numbers here. But I should say that if you're using to apply the work of McQuillan and Yamanoi, then you can definitely get a much better constant than our max d prime and things here. This 2 plus epsilon, this 2 should really be a 1 over the complex numbers. What happens in positive characteristic is, as far as we are aware, completely unknown. Then something that I already mentioned, we need the vanishing of the Kodaira-Spencer map. Or else we have counterexamples. And this is already true in the classical setting of the Mordell theorem in the function field case. And I should definitely say that height bounds have a very long history. And whatever I'm going to say, I will definitely miss at least half of the names that should be mentioned. So maybe I feel I'm better off by not mentioning any names at all. I hope you forgive me. Right. And then if these are the remarks, then how do you prove such a result in this orbifold case? And instead of giving you the full technical proof, I would just spend a few minutes and discuss the classic proof that works without the boundary divisor D. And then finally, in the last section of this talk, I will say what needs to be done to accommodate for D. So let me spend a minute or maybe 10 and discuss how you can possibly find a height bound. And what I'm discussing here is not our ideas. This idea goes back to the proof of the Mordell conjecture in the function field case by Hans Grauert, which was then later refined and improved by Voita, Kim, and again, many others that I should be mentioning here. So the setting is this. We have our X. Now there's no yellow divisor. X is fibered over a curve S, and I have my T. And I want to compare the genus of T with the intersection of T with a relative canonical divisor. And step one is, so let's assume epsilon is given. Then we find a number n sufficiently large and a map, or I should write sheaf morphism, that goes from the relative canonical, but it's n power, into a high symmetric power of omega 1. And by high symmetric, I mean the symmetric power to order 2 plus epsilon times n. And this map exists up to twist with an ample sheaf on S, which I will blissfully ignore for the moment to keep the notation simple. To find such a map is not so hard. This is a matter of writing down Riemann-Roch and comparing the coefficients. Growth order of the coefficients in Riemann-Roch for sections in the Hom sheaf of what I have written here. So let's assume we have found this. And now let's assume that a morphism gamma is given. So if a morphism gamma is given, then we look at the pullback of this sheaf morphism under gamma. So I write gamma upper star of the relative canonical. I write gamma upper star of the symmetric product, 2 plus epsilon n, and then omega 1x. And then I can compose this with d gamma, or rather the symmetric power of d gamma, and go to omega t. And then again, I have a power here, 2 plus epsilon times n. And this is already the solution for most curves. Why is this the solution for most curves? If the composed map is non-zero, then of course the degree of omega x, y, tensor n, and gamma pullback, which is the same as the intersection number t times kx over s, times n, is less than or equals to 2 plus epsilon n degree omega t. And we have compared the intersection number of t with the relative canonical with the genus of the curve t. So we're done in this case. And so for the rest of the slide, I will concentrate on those curves where the composed map is 0. For most curves, it will be non-zero, but there might be some, and maybe infinitely many, maybe countably many, where the composed map is 0. So we will concentrate on curves where composed map is 0. And of course, the question is, what does it mean for the composed map to be 0? What does it mean for the composed map to be 0? And this is maybe the third point. So I observe I have this symmetric power here, which is maybe a little complicated. But let me first say that a morphism from invertible sheaf to omega-1, so no symmetric power, this is a foliation. And the composed map vanishes. Vanishes if and only if the curve T is tangent to the foliation. And that gives us an idea of what's going on if we do have a symmetric product. So a morphism from an invertible to some symmetric power of omega-1, this is a multifoliation. So what do I mean by multifoliation? Well, a foliation is if at every point I specify a tangent direction. A multifoliation is if at every point I specify finitely many tangent directions. And maybe I shouldn't be saying multifoliation. I guess the correct technical word is web. George Pereira is always yelling at me when I say multifoliation because he has written a book where the word web is in the title. And I guess he's right. So, the situation that we are discussing here is that of a web. And of course, the composed map is 0 if and only if T is tangent to the web. So the situation that we are really discussing here is that of a web and curves that are tangent to the web. And of course, webs are more complicated than foliations, but of course, then also, if we have a web, we can always turn the web into a foliation by passing to a cover. So we can turn web into foliation by passing to a cover. Now, we're in characteristic P, and this cover might be separable or inseparable, who knows, if the cover is separable. If that cover is separable, then again, allow me to skip all the technical details. But let me just say that the assumption that the Kodaira-Spencer map is non-vanishing will tell us something about Schoen classes. Then the Kodaira-Spencer assumption gives statement on Schoen classes. And again, that allows you to conclude. If the cover is inseparable, then this is pretty bad. We're screwed. And then I will hardly say anything at all, except that Min Young Kim has devised a way out of here that essentially tells you that the kernel of the differential is not everything and should be seen as a foliation. So let me write down, we need to resort to ad hoc arguments. And I will not specify exactly what those ad hoc arguments are. Instead, I would like to leave it there. So I have hopefully conveyed some idea how the proof works in the classic setup where you do not have a divisor D. And now I would like to turn to the case where I have a D and say a word like how the classic proof needs to be adjusted. So what is the main idea? The main idea in the a case where I have a non-trivial D is that we need to replace the sheaf omega 1x, so the cotangent sheaf, by the orbifold cotangent sheaf of Campana-Pound. And maybe not everybody is familiar with this, although it's becoming more and more a standard. Let me spend a few minutes and explain what that is. In the simplest case, where maybe I have the affine plane, and let's do it over the complex numbers for simplicity's sake. I have C2 and my orbifoldy divisor with a standard coefficient is simply the x-axis, and that comes with multiplicity 1/2. Then what I would really like to discuss here is the sheaf of logarithmic differentials with pole order 1/2. And this is meant to be freely generated by dx and dy, and dy is allowed to have a pole of order 1/2. And the central point in that setting is if I have a curve T like so that intersects with multiplicity 2, 3, 4, 5 or higher. So if gamma of T touches the x-axis with multiplicity 3 or more, then the pullback of this funny form 1 over square root of y dy does not have any pole. Any pole at all. So the poles go away if my curve intersects the divisor appropriately. And why is this cool? To show that this is cool, let me go back to the classic setting, to the very beginning. We started out with this map here. We looked at the composed map, and for things to work, it's very important that this d gamma goes to the differentials on T and not the differentials on T that have some poles someplace. I want the sheaf omega T in order to say something about the genus of the curve T. And the central observation is that in this Campana-Pound business with this Campana-Pound sheaf instead of omega 1, that works. that works because the pullback will be an honest differential and not a differential with poles. So that is the central point, and this is what we would like to do. But of course, there's a central problem to the central point. So central problem. This is a square root of y does not exist. This is a problem if you're trying to build up a theory. But square root of y is well defined on a suitable cover. So, and then here's what we need to do in order to make this baby fly. We need to develop Campana Paun theory in positive characteristic. This is, of course, becomes very interesting in cases where, say, the multiplicity of the device is 1/2 and you're in characteristic 2. Then the covers that Campana and Paun classically discuss. So they always look at cyclic covers or covers that are locally look like cyclic covers. This is, of course, much more interesting because in characteristic P, you have so many more covers to discuss, and to find the right one, to find a cover where everything you want is well defined, turned out to be incredibly hard. And we should definitely say thanks to Piotr Eichinger, who helped us here a lot. And still, we do not have the fundamental answer. We still have developed this Campana-Paun theory in characteristic P only to the extent that was required to prove the Mordell theorem and the height bounds. A full theory that works for arbitrary Campana orbifold is still missing. So that needs to be done. And then we need to upgrade. We need to upgrade the ideas or the approach of Brauer, Kim and Reuter to this setting. So we will be discussing foliations in characteristic P that don't exist on the space where we want them to exist, but they exist only on certain covers that are not very well defined. There's like a large set of covers, and you need to do something that's consistent over all these sets. And as you can imagine, that quickly becomes rather technical. I hope I was able to convey the main ideas, and even though I'm a little early, I think it's better to spare you the technical details because probably nobody wants to see them really. So thank you for your time. Thank you for your attention.
I would like to thank the speaker on behalf of everyone here. Please go ahead if you have any question. Okay. Seems like there are no questions. Okay. In that case, thanks again.
It's been my pleasure. Thank you. All right.
Thank you, Stefan.
Who was this?